Thanks everyone for joining our webinar on running AI weather forecasts in the cloud. This is the sort of second instance of this webinar. We gave another one last week, so had a chance to practice a little bit and iron out the kinks. So you're in for a real treat today. We're super excited about this topic, and we'll dive into it. Okay, so first, just to keep things fun and interactive, here is a video of the forecasts that I generated. I'm trying to slow this down so we can get see what's going on a little bit better. So here are the AIFS weather forecasts that I generated. I don't know how well these videos are coming through on the webcast, but it's really fun to just look at the data, and I'm just super excited about this capability to create weather forecasts on the fly super easily, just from Python. So for those of you who've been in this space, you know what a game changer this is. So that's our topic for today. Oh, I want to advance my slide, not show this again. Okay, so very briefly, just introduction to myself. Who are you listening to right now? My name is Ryan Abernathy. I'm the CEO and co-founder of Earthmover. And I'm really excited to share also some stuff about the platform we're building here at Earthmover. In this talk, I can wear a couple different hats. I'm an oceanographer and climate scientist by training, so I spent most of my career at Columbia University, where I was involved in Earth system modeling, applying AI to various ocean turbulence problems. And so, really wearing my hat as an Earth system modeler today, and excited about some of the new capabilities that these AI models are enabling. And then finally, many of you know me through the Pangeo community. I consider myself a sort of community cheerleader and open source advocate. I'm especially excited about the open source aspect of the AIFS model in particular. I think it's going to do great things for open science and democratizing access to weather forecast capabilities. And so I'll be wearing all these hats at different points during the talk today. A little bit about Earthmover. So Earthmover is a tech startup. We're a public benefit corporation and a mission-driven organization, and our mission is to empower people to use scientific data to solve humanity's greatest challenges. And so at the very top of that list is the challenge posed by climate change, and understanding how to adapt to the changing climate and how to handle extreme weather and all the other challenges that climate change brings is a really strong personal motivation. And I think some of the technologies we're going to talk about today really help move the dial on that. So Earthmover is made up of folks like myself and my co-founder Joe, who have a background as scientists and open source developers, and also folks who have spent time building production-grade infrastructure at some of the top tech companies in the world. And so we're thrilled to be working together to build these cloud-based scientific data platform of the future. We spend a lot of time at Earthmover on open source. So there are 3 projects in particular where we play a leadership role. Xarray is one of our best friends, and that's how many of us met each other at Earthmover, working on maintaining and advancing Xarray, a toolkit for multidimensional labeled arrays and data sets in Python. And we'll see plenty of Xarray in today's demo. Then we've got ZAR, a storage layer for this ecosystem, which is providing cloud-based storage of large multidimensional arrays. And this is very important for this topic. We're going to be using ZAR to optimize the I/O and storage of our initial conditions data sets for this project. And then finally, our new project, Icechunk, plays a key role here as well. So Icechunk is a storage engine for ZAR that provides database-style interactions, ACID transactions, data version control, snapshots, tags, branches, and also really high-performance I/O layer for the ZAR ecosystem. So all of these are components of what I'm going to show today. Beyond this open source, Earthmover is building a platform that really brings all of this whole ecosystem together into a single turnkey experience for managing multi-dimensional array data sets in the cloud. And so here's the sort of architecture diagram for our platform at Earthmover. It runs on all of the major cloud platforms. The base layer is called Arraylake, which is a sort of data storage and management layer, uses Icechunk under the hood to store the data, provides data catalog capabilities, data governance capabilities, and really serves as your organization's single source of truth for your data sets in the cloud. On top of that, we have a new product called Flux, which I'll showcase a little bit later. It provides API-based access to that data using OGC standard geospatial APIs like EDR, WMS, and OpenDAP. And so taken as a whole, this platform can be really impactful in the sort of end-to-end AI ML workflow. So this diagram I'm showing here shows really how you use this platform in the context of the full end-to-end product development experience around AI-based data sets. So, you can ingest your source data into our platform and use it as a base for processing and feature engineering. We can serve training data out of Arraylake with really high performance and focus on delivering high performance data to your GPUs. Same as we'll see today, we can store the data sets for inference, both the inputs and outputs to run model inference in this platform. And then finally, on the data delivery side, you can use the Flux APIs to deliver data to any number of clients, applications, et cetera. And so we consider the webinar today as part of this broader landscape of how do we do efficient AI ML in the cloud with weather, climate, and geospatial data. And so I'm excited to sort of show off some of the stuff we've been building there. Okay, carrying on here. Oh yes, and I just want to shout out some of our fantastic customers, folks who are using this platform today to build AI and ML-driven Earth system data products and use those as part of their critical operations. We love our customers, and the part of the motivation here in this webinar is to help folks like these learn about some of the best practices and implement really efficient workflows in this AI weather forecasting scenario. Okay, so that's my intro. Here's an outline of what I'd like to talk about today. This is a very ugly slide, I realized, and it's okay. It's informative. So first, I'm just going to spend some time talking about AI weather forecasting. What is the technology? What are some of the use cases? I'm going to describe some of the models that are available. And then I'll talk about AIFS in particular and why we chose to focus on that model. I'll describe the workflows involved in AI weather forecasting, specifically training and inference. And I'll look at how you would do inference in the cloud, starting from an ECMWF notebook that they provided along with the AIFS model. We'll do some sort of performance analysis of that notebook and identify some places where we can run a lot. Then I'll shift gears and really get to the meat of the content here, which is the optimized inference setup that we set up on AWS using Earthmover and Coiled to build a sort of full end-to-end workflow for production-grade AI weather forecasting. We'll talk about how we're doing ETL, loading data in, and then the inference pipeline itself, and describe some of the optimizations we made to shave 90% of the runtime off of those inference workflows. Finally, we will just as the icing on the cake, show how we can use Flux, our API layer, to connect those outputs directly to APIs and view the outputs of our inference immediately in a web map or in any other sort of API query context. Finally, we'll wrap up, review what we did, and look at explain how you can get started by doing some of the same type of stuff. Okay, let me get going here. All right. Next slide. Okay, so let's now have the sort of lecture part of the webinar here. I'm going to put on the professor hat and talk a little bit about how weather forecasting works. Looking at the attendance list, I know we have a lot of experts on this topic already in here, but hopefully it's useful to review some basics and sort of set a baseline and talk about why these AI models are so exciting. So conventional weather forecasting works basically the way I'm illustrating on my slide here. We take, or by we, I mean the big meteorological organizations like National Weather Service in the US or ECMWF, sort of bring together all the available weather observations from satellites, from soundings, from weather stations, and they integrate those through a data assimilation framework into a general circulation model. Essentially a model, a physics-based model that solves the equations of fluid motion and thermodynamics on a grid within a supercomputer. By combining that model with all the available observations, we sort of get a best guess estimate at the current state of the atmosphere. That's called the analysis. And then we step that model forward to produce a forecast. And we can also take that, historical data and use it to produce a reanalysis. So this is how weather forecasting has been operating for, the past 50 years or so. And it's been incredibly productive and successful. These data assimilation-based weather forecast models have continuously improved their skill and provide a huge amount of value to society. They are, however, very exclusive in terms of who can actually run and do this type of weather forecasting, because it requires a lot of data to be input, and it requires a big, expensive supercomputer and a lot of infrastructure to keep everything running and deliver the forecasts in a timely way. So this is just a nice figure from ECMWF that shows the sort of ongoing operational nature of weather forecasting. In this case, we are taking observations, and producing an analysis every 6 hours that's used to produce a forecast of various ranges from short term to much longer term. And this is just running continuously, constantly at the weather forecasting centers, and that data is made available in near real time to users. So by now you've probably heard of AI weather forecasting. So AI weather forecasting is hot. It is a really exciting application of deep learning. And there are all kinds of new AI weather forecast models available out there. So here I'm just highlighting a small selection, some of the ones that I'm aware of. Google's GraphCast, NVIDIA's Earth-2 are two from big tech. There's also a lot of startups working on this. Salient, Silurian, Xcarta, Jua, Brightband, Zeus AI, all of these companies are developing novel AI-based forecasting methods with slightly different focus and different objectives, which nevertheless create a huge amount of new options for folks who are interested in weather forecast products. Whereas, just a few years ago, it was really just the main government-based players providing this type of forecast product. So how do these models work? First, want to make a disclaimer. This is not intended to be a technical talk on sort of the deep learning science of AI weather forecasting. Just trying to sort of define the basics here and set a baseline. So for the most part, these AI weather forecast models are all different flavors of deep learning based on deep neural networks. But within that, there's a wide range of different architectures that are being used. And this is a super active topic of research today. And so whatever I say, I'm sure someone out there is working on a model that, doesn't fit the mold that I'm describing, but, this is just a summary here. Now, a very popular architecture that was popularized by GraphCast and its predecessors is this sort of encoder, processor, decoder architecture, where we're starting with input data that lies on some standard spatial grid, and that is encoded into a latent space. There is then processing done on that data in latent space, and then the results are decoded back out to physical space. So this is how GraphCast works. This is how AIFS works. There's a growing number of foundation models that are also becoming popular here. So for example, the Aurora model from Microsoft. One thing a lot of these models have in common is that they're typically trained on reanalysis data, such as ERA5. And so already this tells us something quite important, that the AI weather forecasting project, at least for this class of models, is not really independent from the conventional weather forecasting model world. It still depends on products of that data assimilation-based weather forecasting, such as the reanalysis, in order to provide the training data. So in some ways, you can think of these models as a flavor of emulators of the conventional models. That being said, they often have skill equal to or better than the conventional models, which is what makes them exciting. But most importantly, they can run in inference mode very cheaply. So using, many cases, just a single GPU, you can make a whole AI weather forecast on a single computer. And that capability in particular is quite transformative in terms of what it opens up for democratizing access to AI, to weather forecasting. This is just saying what I just said through a slide here. Conventional forecasts generally have to be run on a big supercomputer, and not a lot of organizations can afford a big supercomputer. However, AI weather forecasts can run on a single GPU in seconds, and so that is enabling all kinds of new organizations to actually make their own weather forecasts, where before that was quite impossible. Some of the use cases for these AI weather forecasts. We're certainly seeing a lot of interest in this capability from folks in the energy trading space. So energy trading depends very heavily on the weather for both supply and demand of renewable energy. And so tailored forecasts can really help such traders make better trading decisions and do all kinds of optimizations. There's a strong use case in sort of logistics and supply chain, understanding how weather may disrupt transportation, influence supply chains. So this is allowing folks in that space to make better plans and optimize more effectively. Insurance is certainly an area with a very strong use case for this technology. Being able to define custom forecasts to model and predict risk on loss from extreme events is certainly an area of active exploration and research today. And finally, there's a whole research angle to this, right? So just being able to run weather forecasts very quickly and very cheaply has the potential to help us develop a much deeper understanding of the Earth system by running larger ensembles, by doing more flexible experiments. So just as a research tool, these models are very exciting. Okay, so now let's talk about AIFS in particular, because I just rattled off about a dozen different AI weather models. Why are we focusing this webinar on AIFS? Well, AIFS is a state-of-the-art AI-based weather forecasting model that uses the encoder, processor, decoder, graph neural network architecture. AIFS produces and consumes data on the standard ERA5 N320 Gaussian grid, which has approximately 31 kilometers resolution, so relatively high resolution on a global scale. In the words of the developers, AIFS offers a step change in forecast skill compared to IFS, the conventional weather forecast from ECMWF. It does up to 10% better on many scores. And so what I'm showing here is, it may be a bit hard to read, but we're looking at the root mean square error of surface temperature, with AIFS being in blue, so lower is better. And this is the forecast time, so going out to 10 days here. And we can see that, yeah, this is the red line is IFS and the blue line is AIFS. So it's demonstrably better at forecasting surface temperature and many other variables. Although I should caveat that it's not always so ambiguous. Precipitation is much harder, and there are other metrics where the skill is not necessarily so high. Beyond the skill of the model, I really believe that whoever's at the top of the leaderboard, this is something that's going to fluctuate from month to month in this space. We're seeing a lot of competition. So, I think there's a lot of other factors to focus on when you're looking for an AI weather forecast model. And here, it's important to note that AIFS is an open source model. The source code is open, and the weights are open. So many of the AI weather forecasting models from the big tech companies, the weights are available, and they can be used for non-commercial purposes like research, but they can't be used in a commercial context. Whereas AIFS is licensed CC by Creative Commons Attribution License, which allows anyone to use this model basically for anything they want, as long as they attribute it to ECMWF. It's also got great documentation. It's very user-friendly to use. And I see this just as part of a broader movement underway at ECMWF that's really embracing open science. We can see this in ECMWF's open data program and in efforts like EarthKit, Anemoy, et cetera. So it's awesome to see an agency like ECMWF really embracing open science and providing all of these powerful tools and data sets in a way that makes them really easy for anyone to use. Okay, so let's talk a little bit about the workflows associated with these models. There's basically two main workflows that are associated with AI weather forecast models. One is training. So, these models ultimately are driven by fitting themselves to data. They're trained to reproduce the correct forecast by showing them many forecasts over and over until they get it right. And that produces a data set, which are the model weights. And that is generally a pretty expensive process. It takes a big GPU cluster running for a long time to train one of these models. But that's not something just everyday users of the model have to do. ECMWF has trained the models and they publish the weights, and those weights are freely available under a permissive license. And so we can just go use the model in inference mode. So inference is when the model is rolled out in forward mode, given some initial conditions to produce a new forecast. And this is relatively cheap. It's still not trivial, but it's relatively cheap and can be done by anyone pretty easily. And this is what our focus is for today. We're going to be running AIFS in inference mode and using it to produce new weather forecasts. And not just current weather forecasts, but actually historical weather forecasts that we can use to evaluate the skill of the model against our own training objective, our own validation objective. So as a starting point for this inference, we looked at what ECMWF is providing. And in fact, I can just go straight to this and look at the repository for AIFS in Hugging Face. This is a great resource. There's a lot of useful information about the model. And we can go in and we can get a notebook, run AIFS v1, that tells us exactly how to run the model and to make a new forecast. And I think this is a fantastic starting point. I'm really grateful for ECMWF for providing such a useful starting point. When we got our hands on this notebook, we still had plenty of questions that I'm sure you may have if you are trying to do the same thing, right? So first of all, well, where can we actually run this? There's a link to open this in Colab. That's nice, but when I tried that, the Colab GPU that I could get didn't have enough GPU memory to actually run the forecast. So, what sort of environment and hardware is really needed to run the model effectively? If we don't just want to run this model sort of one-off, how do we actually orchestrate an inference pipeline where we want to make a bunch of forecasts automatically rather than running an interactive notebook? How should we set that up? Presumably, we also want to store the results of these forecasts and do something with them. And so, how should we do that? Where should we save those results, and how should we do that in the cloud? And then finally, top of mind for many folks, I said that inference is cheap compared to training, and that's true. But inference still requires a pretty beefy GPU. And so, if we're going to get a bunch of GPUs in the cloud, we can quickly rack up a pretty big bill. So how can we optimize this notebook to keep that GPU as active as possible and optimize both our performance and our cloud GPU bill. So these were all some of the questions that we thought about when we started down this path. And we did a performance analysis of the original notebook, just running in a vanilla environment in AWS. And what we found kind of surprised us, which is that the original notebook spent over 2 minutes downloading and reading GRIB files while the GPU was just sitting idle. And running the forecast itself, in this case, we ran a 48-hour forecast. It only took 10 seconds. And so, you know, this is not an efficient use of GPU to have the GPU be waiting on data. Unfortunately, this is a really common pattern that we see whenever we look at AI workloads, is that folks are having a hard time getting the data throughput they need in order to keep the GPU busy. And this is, of course, a problem we're quite obsessed with at Earthmover, something we work on, you know, and have thought a lot about how to optimize for. So this is immediately where we wanted to dive in. So in what remains, I'm going to describe a cloud-native data infrastructure we put together in order to do these AI weather forecasts. The tools we used to do this were AWS, so we're going to be running all of this in AWS. And on top of AWS, we use 2 additional services that just make the development experience way simpler for the user. One is we're using the Earthmover platform to manage the data, both the initial conditions data and the output data for the forecasts. And this gives us both really high performance I/O to help make those GPUs go faster, and also a really robust central source of truth that's fitting for a production grade pipeline. It's a lot more like a database than a pile of GRIB files. And then we also use Coiled to help us orchestrate this GPU compute and make it really easy to launch GPU jobs in the cloud and set up the appropriate Python environment to do our computing. And so with these 2 services, we're able to put together a really simple and performant system. I'll say just a word about Icechunk and how it figures into this. So all of the data for this project are stored in Icechunk format within the Earthmover platform. So Icechunk is a relatively new project. I encourage you to check it out. Go over to GitHub and give it a star. Icechunk is a transactional cloud-native storage engine for Zara. So it was designed from the ground up to give high performance with object storage. It provides ACID transactions. So whenever you update data through Icechunk, it happens in a database-style transaction, which produces a ton of additional robustness and safety whenever you're running data pipelines. It also provides data version control and virtualization capabilities over existing file formats like NetCDF and GRIB. It's compatible with Xarray, it's compatible with PyTorch, TensorFlow, and all of the different deep learning libraries you might want to use in this type of workflow. It is implemented in Rust, but there's a Python wrapper, and it's 100% open source. We also use it within the context of our platform as the core storage engine. Here's just some results that we obtained through a previous pilot with NASA, where we were just looking at the raw I/O performance of how quickly we could read data from object storage and load it into memory for analysis. In this case, we were focused on the time series extraction problem. How can we get a time series out of a stack of NetCDF files? And we found we were able to accelerate a typical workload by 100x or more using Icechunk compared to other technologies. So we're very excited about this, and Icechunk will feature heavily in the demo that I'm going to show. Okay, so the first step of our pipeline here is to actually separate the initial data loading from ECMWF Open Data into its own job. The idea here is, these forecasts are initialized from ECMWF Open Data, which is distributed as GRIB files. Yet we found, even with those GRIB files sitting right on S3, the way we were loading them and downloading and loading that data, it was not really fast enough to keep the GPU busy at all. So we decided we would extract that data and prepare an optimized data set of initial conditions and store that data set in the Earthmover platform. And we orchestrated this using Coiled by just launching a bunch of ETL jobs to extract these forecasts and store them into the platform. It's relatively slow. You know, those jobs kind of just have to sit there and download data and write it. But it's also cheap because we're not using a GPU. We're just using cheap CPU spot instances. And so this pipeline, we were able to scale out and process all the data we needed to and land it in a highly optimized form. And just to give you a sense of what the results of that look like, I'll take you on a tour through the Earthmover platform. So this is what, I want to go to Earthmover Public. So this is what an Arraylake organization looks like. This is our sort of home for our data in the cloud. It sits on top of cloud object storage. So we've got a range of cloud storage buckets that are attached to this account. And then we've got data stored in these repos or repositories. And in this case, these are Icechunk repositories, not GitHub repositories. And so here's the AIFS output. And you can see here, we are just essentially building up an archive of forecasts. If we go look at one of these, we can see these forecasts. We have one every 6 hours, and we're storing this in a way that's, these are the outputs. I'm on the wrong thing, sorry. That's the end result of our forecast. Here's my initial conditions data. So it looks very similar in many ways, except these are just optimized input fields designed in a format where I can load them straight into the model. And so when I go run the demo, you'll see what I'm talking about. So this is the ETL step, and in a minute I'm going to actually walk through the code we use to do that, but I'm just giving you a high level here. Step 2 is inference. And so when running inference, we are then loading data rather than from grid files from the Earthmover platform, where we can load those initial conditions very quickly, initialize the forecast job, and have it run super quickly as well, and save the outputs, again, back into the Earthmover platform, and have all of that I/O be super quick. Now, those jobs are much more expensive because we have to use a big fat GPU, but we've optimized them heavily, so we are spending as little money as possible to do a lot of forecasts. So specifically, there are a couple key performance optimizations we made to really bring down the runtime of these jobs. The first was simply replacing the loading of initial conditions from the grid files to loading them from Icechunk in our platform, and that brought things down from 2 minutes to 1 second for the data loading. Another trick that we found is that we wanted to regrid the outputs of the model onto a lat-long grid so we could analyze them more easily, rather than leaving them on the Gaussian grid. And originally that was taking 20 seconds using the EarthKit regridder module from ECMWF, but we found a way to make that regridding run on the GPU, which then shaved another 20 seconds off of our runtime. And then finally, we interleaved the output storage with the inference in a separate I/O thread so that those two things could happen in parallel, and we didn't have any overhead. We didn't have to wait around to write outputs before we could keep our forecasts ready. And so with all of these improvements, the cost for producing a 48-hour reforecast for an entire year dropped from $146 to $19. And also just ran a lot faster. So at this point, I'm going to walk through some of the code that we developed to do this. I'm going to start by just running a notebook that shows, what the original data loading was like, and then what the optimized data loading was like. And I'll do this from a notebook in the cloud. And so, let's see, I'm just going to scroll up here, and I've got these rather large widgets here. But the point here is, as long as I'm running this, we can see that our GPU is just sitting there idle. Right, and so when I run the original ECMWF notebook, it has to do these data downloading steps, extract data from, in this case, the data is all in AWS, but it still has to be downloaded. I'm not going to run all of these steps here because it's going to take a while. The one that takes the most time is the pressure levels. Instead, I am going to just go down to the place where we are connecting to the Earthmover platform. I believe I'm already logged in, so I don't need to rerun that step. I'm going to connect to this AIFS initial conditions repo here, and then I'm just going to load the data into memory. And we see in this case, this is taking 1.42 seconds to load all of the initialization data we need to initialize a full run. And at that point, we have to do a little bit of light pre-processing. And I can see I got an error because I didn't run this earlier cell. That's the perils of doing a live demo. So I'll run that. And then I will just start this runner. I believe I have to use input state 2. And now we'll see finally this is going to start running, and we'll see at some point our GPU will become active or not if this dashboard decides not to cooperate here. Yeah, it looks like my GPU meter has decided not to play right now, but you get the point that, you know, only once the data are loaded are we able to start inference, and that's why the original job was taking so long. So I'm now going to switch over to the GitHub repo and just walk you through the environment that we, the setup that we use to create this inference pipeline. So first, I'm going to start from here where we're creating an optimized software environment to run these jobs in. So Coiled allows us to really easily define a software environment, and we have two separate ones. One, a big fat GPU-enabled environment, and another very lightweight environment that we're just going to use for the ETL. And so when you go look at this environment file, you'll see, in particular for the GPU environment, we used Conda to install this, and quite a bit of tweaking was required to find the right packages that would make AIFS run happily. You know, we need a certain version of PyTorch, and we need this flash attention package, which is actually quite tricky to install. So hopefully this environment that we have put together here is helpful for other folks who want to get started with this. We spent quite a bit of trial and error trying to find something that would work, but finally we ended up with something that worked. Now, in terms of actually running the model, well, it all lives in one simple script, which we call main.py. And this is accessed just from a command line. So you can just run either ingestion, specifying a start date and an end date, or forecast, specifying a start date and an end date. And so this forecast step, what it does, I'll just really walk you through the most important function here, which is run single forecast. What this does is it takes a date that we're running the forecast for, a source session. So this is the an Icechunk session that describes where our data are coming from, and it loads the initial conditions from that Icechunk repository, creates an initial state vector, sets up a GPU regritter that we're going to use as part of our ingestion process, or sorry, as part of our output saving process. Now, here's a trick that we developed in this thread, in this example that you might find useful, but we decided to use a separate thread for the output. So we want to save the outputs of our weather forecast as the model is running, but we don't want to block the forecast in order to do that. And so we use this pattern where we actually have the writing happening in a separate thread. We create a queue and a worker that takes items off that queue and stores them. And we run that in a separate thread. And then here in our main forecast loop, we are just running the forecast, converting it into X-array, an X-array data set, and then putting that into the queue to be stored. And when this is finished, we join the queue, everything finishes up. And so that's one single forecast. And then in terms of running this and scaling this out, we spin up a DAS cluster using G6E 2x large GPU nodes, and we just have this pipeline. We just throw jobs at it and run these forecasts, and they all run on this cluster. We can use as many or as few GPUs as we like. And I believe I have the results of one of those running. So here, I just ran this in Coiled. I don't have a dashboard going, but here I was using 10 workers, and it cost me $5 to forecast a month's worth of forecasts. And that ran 120 different forecast tasks. Been running these sort of continuously all day. So as a final step here, we're just going to load up the results of the forecast that we just made. So where did I put this? Sorry, I've just minimized the thing I'm looking for. Okay, great. I think, okay, I'm getting a little bit lost in my tabs here. So the results of our forecast have gotten stored to this AIFS output directory or repository. And here we can see a whole history of all these forecasts that we're running. This is just part of how Icechunk and Arraylake work. We can see a full version history. We can see everything that was actually modified in one of these specific runs, and we can see all of the different arrays and groups that were written as part of each commit. Now we'll go in, open up another Python notebook, and just open up those outputs. We'll get one of these repos from Arraylake, and we'll just plot it up, and we'll look at some of the results. So here is a total precipitation field. This is the forecast we just made. It's available instantly to us. We can plot a sort of time series of a forecast. Here we can see a precipitation forecast for a specific location. We can also use the Flux APIs in order to create a nice web map where we can interact with those precipitation outputs in an interactive web map context. And so that makes it really easy to build dashboards and other sort of things on top of these forecasts. And then finally, if we want to pull out our forecast data in another format like CSV, this is where Flux makes that also really easy to do. So here you can see I'm just querying one of these forecasts for a specific date and asking for data at a specific point and asking for data in CSV format, and I can just pull that right out of this immediately. So just to sort of put a bow on it, this last step I showed is really, once our data are in Arraylake, they're accessible to be used with Flux. Flux is a high-performance geospatial API gateway that serves our data back out through a range of different geospatial API protocols. So that's how I was able to make that Slippy map. That's how I was able to pull out CSV data. So the idea here is that if you're storing this data in the Earthmover platform, it's immediately accessible and can be integrated into applications as soon as those forecasts are ready. And this is really key for folks who are looking to operationalize these forecasts, integrate them into downstream systems, et cetera, as opposed to just dump a bunch of files into a drive somewhere. Okay, so I'm wrapping up here, and we're going to have plenty of time for questions and discussion. And so I would like folks to start thinking of any questions that you want to ask. But to summarize, we started from ECMWF's amazing open source code and models. And I just can't say enough good things about ECMWF and their approach to putting this stuff out there. It's an incredible resource, and we're thrilled to be able to benefit from it. We developed a production-grade setup on AWS using Earthmover and Coiled, and this included both an ETL pipeline to prepare our initial conditions data and an inference pipeline to run the model in inference mode in an optimized way. We stored those optimized initial conditions in the Earthmover platform and also stored the outputs of our forecast. And through a series of optimizations, performance optimizations, we were able to reduce the cost of that inference by 90% compared to where we started. All of this stuff is in this open source repo, the AIFS demo, if you would like to play around with it and adapt it and use it however you like. And just as a final plug. If you are working with weather and climate data in the cloud and you're looking for a solution that provides sort of turnkey, out-of-the-box data management, data governance, and API access, we'd love to talk to you. Feel free to just shoot me an email or head over to our website to learn more about our platform. So I will wrap it up there. I'll leave the summary slides on, and I would love to get questions, comments from anybody. You can leave a question in the chat. You can just come on camera, unmute, and just start talking. Really, I welcome any form of feedback, and yeah, the floor is yours. Okay, Rakshith is asking, how do I adapt this workflow to an HPC? I wish I had a better answer for you, Rakshith. We're really focused on the cloud workflow. None of the main tools that I was using here, Coiled and Earthmover, are really designed to work on an HPC cluster. On an HPC cluster, your general pattern is going to be to download the data to a file system and create batch jobs that are going to run the forecast in your HPC cluster. And each HPC is going to do that a little bit differently. You could still use Icechunk to store the optimized data on your HPC system. And I think that would give some good performance benefits compared to using the GRIB files. But overall, the architecture is going to look quite different the way you're going to orchestrate a pipeline. That being said, that's how ECMWF runs their own forecasts, right, on an HPC cluster. So I think there's plenty of resources out there to support that and to support you. That just isn't really where we focused. We're seeing a lot of interest in using the cloud for this type of workflow. And so that was the emphasis today. So Fiaz asked a great question. What about workflows to fine-tune the ML model, integration with PyTorch and JAX? So this model already runs it's a PyTorch-based model. And so we're using PyTorch under the hood, but yeah, we didn't do any tuning, training, or fine-tuning. Now, ECMWF has some fantastic resources for that as part of the Anemoy project. And so if I would go to Anemoy, I'm going to just pull up the link for you on, let's see, Anemoy training is probably what you want. I'm going to drop this in the chat. This is probably the best way to learn about training and fine tuning. And I would note again, like, for training, probably even more than inference, loading data is going to be a huge bottleneck. So if you're doing training and fine tuning, you really want to make sure that your data loading pipeline is highly optimized, because that's going to give you the most efficient utilization of the GPU. Anybody else? Come on, somebody come on camera and ask me a question live. Otherwise, I'm just sitting here talking to my blank screen. All right. Thank you. Go ahead.
Hi, Ryan. Great presentation. I was wondering, as a climate scientist, what kind of interesting things that you're expecting to see in terms of applications of that, not only for the weather forecast, but also for research. And if you have any examples of groups that are trying to investigate the latent space and the weights of these models, and if it can bring any insight about the physics.
That's a great question. I think, without a doubt, there's a lot of folks who are working on that problem, trying to understand how to interpret these models, what the latent space means, and using them as a tool for research. I see just at a very basic level, the ability to initialize a forecast from any state of the atmosphere is a very powerful research tool, because that allows us to ask questions around attribution of extreme events, understand the predictability of past events, right? Could we have forecast the impacts of, Hurricane Sandy better in New York? Just to be able to make a weather forecast just like that without a big cluster, that is just so democratizing that I think it's going to open up all kinds of different research applications. So I know that's a little bit of a vague answer, but I think the space is very broad.
Thank you.
Yeah, no, go ahead, Megan.
I wasn't sure if there was another person with their hand up, so if not, then I'll go. Okay, first, nice presentation and fantastic job in optimizing the workflow and also showing I/O is the major bottleneck in both inference and training. So I was wondering, you mentioned like multiple, you can request for multiple GPUs, and if I understood correctly, you're using Anemoy under the hood. So does it support the distributed inference, or is it essentially like doing multiple inference at the same time with multiple GPUs?
Yeah, what I'm doing is very simple. There's nothing so sophisticated as multi-node inference. It's just an embarrassingly parallel running the inference in parallel. And what I'm doing here is I'm not just running a single forecast. I'm actually reforecasting the entire year, right? And so I think I should have been more clear about that up front. One of the cool things about this ability, and this is related to Andrew's question in the chat, is we see folks who are interested in using these models. They're really interested in doing heavy validation, and not just against a generic metric, but often using a very custom metric. So say you're a solar operator in Europe, right? What you really care about is the ability to forecast the thing you are interested in, which is your generation capability, stuff like that, right? And so to be able to create a big historical forecast archive and understand the skill of the model for your specific application is really valuable. And so that's what I was doing. I was running, hundreds of different inference jobs all in parallel and producing a whole data set of the outputs.
And that actually works perfectly for a lot of like ensemble run types that requires a lot of like inference jobs to run in parallel, but not like any distributed essentially. Because those types of distributed inference are usually good when it doesn't fit on one GPU, and usually like for at least like weather and climate, everything for inference, it fits nicely on one GPU with enough memory. So.
Correct. If you wanted to run inference with the state-of-the-art LLM, like a big llama model or something, you would need multiple GPUs and have to run the cluster just to run inference. That's definitely not the case here. These models are small enough. And in fact, we spent quite a bit of time figuring out what is the smallest GPU we can get away with in terms of GPU memory. We needed about 40 gigabytes of GPU memory to get the model to run. And so we found one that was a good cost and performance trade-off, and it's documented there in the GitHub repo.
Perfect. Yeah, that's 40 gigabyte. Yeah, that's the threshold that we see as well. Perfect. Thank you so much. Awesome.
Yeah, no problem. Okay, Andrew has a question in the chat, then I'll go to Ian. So Andrew said, what does validation of the output data look like? How would you ensure that the output is realistic? Great question. Fortunately, the ECMWF folks have done a ton of really rigorous validation of this model before they released it as version 1.0. So we know that in a general sense, this is a highly skillful model. However, as I mentioned, anyone who's using forecast probably has a specific metric in mind. So, part of what I'm trying to show here is how you can run the forecast and then define your own metric. Maybe you care a whole lot about precipitation in Arizona, and that's really what you want to evaluate, and you want to compare the skill of AIFS versus GFS and HER and all the other models. Great, so this allows you to do that, and absolutely validation is really critical for any application like this, and should be done very rigorously and carefully. Ian, go ahead.
Yeah, hey. it occurred to me during the last question that obviously, like you mentioned, the kind of ability to run these things on a single laptop takes out a ton of the effort and compute cost needed that kind of relegates former forecast or non-AI forecast to large institutions. And I guess now you mentioned you spent a lot of time kind of tuning the size of the instance you were using, a lot of time setting up the environment, et cetera. Are there any tools either with Earthmover or Coiled or any other tools available that kind of help that step from taking a lot of time in sort of the exploratory phase of using these models?
So you're asking if there was a tool that will help you define the environment and figure out the optimal set of parameters to use to run your job?
Yeah. It's a bit of a tough question, but yeah.
It's a kind of meta question, you know, and I would say, no, I don't think there's a tool that does that. I don't think that there's enough different options around this to have a need for that kind of tool yet. I think what we're trying to do is just provide a really ready to use, fully baked example with this, you know, and that's my experience with a lot of things in AI in general. Just having a fully baked end-to-end example goes a long way towards enabling people to actually use that. Now, we already started from a great example from ECMWF. I mean, that notebook that they provided, it ran perfectly out of the box once we got the environment configured. And so, you know, huge kudos to them. They made it already really easy to start. And so we added a little bit of optimization on top of that and sort of packaged it together. And so hopefully this is going to be a starting point for others to build on. And, you know, I think, you know, that optimization work is often highly customized to the specific needs of an organization. Some are more cost conscious than others. There's different things to optimize for. So I don't think we're quite there yet, but just trying to get more examples out into the open, I think helps a lot. Okay, let's see. Judy has got a question. Does the Earthmover platform plan to include other data sets like depth analysis and forecasts or other AI models like Aurora? We're exploring this right now. You know, our platform, we're primarily focused on giving you a place to store your own data and build your data product. However, we're seeing a growing demand for analysis-ready data that is just packaged and ready to go and integrate into, you know, workflows and applications. So that's something we're exploring, Judy. And if you have a need or a use case around that, we'd love to hear from you. So we might actually follow up with you and hear if there's some specific data sets that you're interested in that would help you go faster. Okay, well, I think this brings us to the end of our hour. Oh, Yuri's got one more question. Ocean models. It's a great question. Yes, there's absolutely folks working on AI-based ocean models. We actually had the same question at the last webinar, and I'm blanking on the name of it, but yeah, ocean, a little bit behind in terms of commercial application, but we're definitely getting there. Okay, thanks, folks. This was a lot of fun. Thank you for coming out. Really appreciate the opportunity to share. Don't hesitate to reach out if you have questions. And yes, have a great rest of your day.